Ótimo. Oh, sorry. Wrong language, sorry. um, okay. So, first of all, I'd like to thank you for the invitation to speak here. It's an honor. It's always great to be here and talk to all of you. My name is André Martins. I am a professor at USP Leste, at the new school of USP here in the capital, but in the new campus. We are about to be 20 years there next year, so it's not so new anymore. I'm there from the day one, and we created a group that works with complex systems there and things like that. So we had a lot of problems making it grow and things, and problems with the campus that was closed for some time, but that's not the point. When Marcus invited me to talk here, I saw that it was about networks. And while I use a lot of networks in my research in opinion dynamics, I'm still to make anything that's relevant to network theory, okay? But I do have some interesting results related to how opinions spreads over networks, including basically using a model that I created from and published 18 years ago, and then I have been working with it since then. So what I'm going to do is talk about that, and especially the title of this lecture is about one paper where I combined both the spread of opinion and used that to make one simple network that evolved with time to see what happened when opinions influenced that. It's just the first step, very, very simple, but that's what I'm going to talk about. And I decided to include the mathematical steps of my opinion model because although they are very easy if you know what you're doing, they are not usually something that we see when we do physics. So I'll go there. So in the area of opinion dynamics, we have some very typical problems that are if your system will go to a consensus, if everyone will eventually agree or not, okay? How long will it take? Because sometimes you have a system that will go to consensus, but it will just take 2,000 years. And from any practical point of view, it won't happen, okay? Will a society remain polarized, as we have seen in Brazilian elections, North American elections, and many other places around the world where the debate is becoming much harder, and people are starting to distrust the other side and becoming unable to speak with the other side and becoming losing trust, completely losing trust in what the others might say. And it doesn't mean that you have to agree with them, but sometimes the other side might have a valid criticism. Even if you're right, in overall, they might point you that detail where we were wrong. So listening to people who disagree with you is actually important, even if you are right. Okay, so this break of the debate in our democracies is a very, very bad thing. Even if you're sure about your point of view. So what creates extremism, how to avoid bad consequences. And extreme opinions, that was how I started with this here. Can lead to some problems. Of course, not every extreme opinion is a bad thing, just as not every cascade is a problem. Okay, depending, you can have you can be sure of something. If you are sure you should not jump from the 24th window, that's a very good extreme opinion to have. Okay, but they can lead to violent behavior, to lack of trust, as I said, to problems like acceptance of vaccination. We saw that here all over the world, things that we took for granted, that we trusted the community, the scientific community, that they were doing a good thing with vaccination, and people start doubting that because of political reasons, not because of problems with real problems with vaccines or real problems with the data or real experiments. Climate change, the same thing. The first prediction of climate change is more than 100 years old. And yes, at that time there was a lot of doubt. We could not be sure at all. But the data is, is consistently agreeing with the predictions. So there is a point where it doesn't matter what your political point of view is. You should look at the data. And you should listen to the experts. And if you have but these things interfere because of human biases. And we tend to buy ideas as a package. And then because we agree with one, we tend to agree with many others and things like that. So to work with that, I wanted to understand this problem. Polarization is an important part of what I'll speak here. There are many things that generate it. First of all, there is a problem of homophilia. People tend to interact with people that are similar to them because you went to the same university, you were born in the same neighborhood, you are of the same family. So people we interact agree with us much more than the rest of the society. Okay? So just that tends to... There is also confirmation biases, even if you try infographics. But if people are looking for information that agrees with them, and so we are all fully connected here. But I start asking who agrees with me and then only listen to them. Okay? Oh, okay. Then this will reinforce and they will create bubbles of opinions. This could also mean that even if I listen to everyone and do not shop for, but it's unavoidable that I will trust some people more than I trust others. Okay? And if my trust depends on what they think, I will unavoidably start to accept more the people and trust more the people who think are already like me. So we have a problem. And then there is also a problem that is more related to us here. That is where you search for similar minds and you create your network of influence from people who already agree with you. And those who do not, you disconnect. So the paper I want to speak in the end is about this, about this tendency and what effect it has over a network on when I get that. But to get there, I have a lot of things to talk first, okay? First, I will talk about my initial model for opinions, because it has some very interesting features that I think other models are... my model is also a toy model, okay? All of these models in opinion dynamics so far today are toy models. None of them are perfect representations of what happens. Forget about that. But some of the models are better to represent one type of situation. For example, if we're talking about discrete opinion models, and here physicists that are basically working on this because you can represent that as a spin and use everything we know about spins to model those and make a lot of things. They are very, very useful if you're talking about choices. What I choose, I pick A or I pick B, -1, +1, -1, okay? Well, I could have a Potts model, or I could have 4 choices, but they are good to represent choices. Will I vote for A? Will I vote for B? If there are more alternatives you can put there, more possible spins, but they do that well. But they do not tell me if my opinion is strong or not. You do not have implicitly. When you make a spin model, you do not have a strength to, oh, my spin +1 is stronger than Marcus, for example, or is weaker than his. We are both +1, so, and that's that, okay? On the other hand, you have other type of models in opinion dynamics, and these are more common in the computational scientists from the computational science, there are continuous models where they represent an opinion over a range 0 to 1. And then typically you introduce the threshold. So if we disagree, if our opinions are a distance that are larger than 0.2, per example, we do not influence each other. Or we could be that we influence less, you could change the models. But then you have different type of dynamics. And these are not so good to speak about choices because you have a continuous range. You would have to put intervals there. But speaking about strength of opinion here becomes more natural because you can say that you are close to 0 or close to 1, or you are a central opinion. There is a problem here that I noticed later in doing work that I will just pass very fast, because there are actually two types of extremism that we might want to consider. One is if your opinion is close to 0 and to 1. And the other is if you are able to change your mind. Because even if your opinion is very close to 0, but you are accepting influences from people who think very differently of you, you might change that very fast. On the other hand, if your opinion is 0.5, you are a centrist, but you only listen to people who are 0.01 minus 0 and 0.01 above you, you will not change your point of view, or you change it very, very slowly. So there is actually some things hidden here that are not usually debated, and that is what I actually mean by extremism, okay? We have to decide that in each of our models. But anyway, as an approximation, we have these typical things, where here we have discrete models, 0 as an minus and plus 1 are black and white, and you can have, depending on the parameters, you can have a voter model and people will slowly agreeing with their neighbors, and then just by random, one opinion wins in the end. And you can have this that I taught you, the opinions would go from 0 to 1, and depending on how, and this threshold of how much they trust each other, how much they agree, how far you have to go for agreement. If the agents are very strict, you might have many surviving opinions in the end, or if they accept the influence from other agents who are farther apart, you can have everyone converging to consensus, okay? So what did I do about that? We had this model that has a strength of opinion. We had those other models who have very well-defined choices. I thought myself, well, I can do both. I will introduce both. How will I do that? I created a model where I have a probabilistic opinion associated with my spin. So above two possible choices, A and B, plus 1 minus 1. And if my probability that A is the best choice is larger than 50%, I choose it. If not, I choose the other one, okay? The spin system, just a normal spin system. But since it's a probability, I can be more or less certain of it. The actual dynamics happens over the probability. And then, that's why I started this. And then I can speak about, in the end, the model I got was a very simple, additive model. I will talk about probability in a moment. But the end model was that. I add or subtract 1. If my variable is above 0, I make one choice. If it's less than 0, I make the other choice. What happens? I have the possibility of choice because I have positive and negative. And I have strength of opinion because my opinion can be plus 1, but it can also be plus 100. If my opinion is plus 100, I'm 100 steps away from changing it. So I will not change it easily. But how did I get there? Because this model already gives me a situation like this I show here, when you have frozen realms of opinion for one and for another, and they started locally reinforcing. The first implementations I did for this model, I did over a square lattice, very basic square lattice, not even periodical conditions. But you see that they start forming domains as in the Volter model, but those domains freeze because there comes a point when almost everyone is listening only from people who agree with them, or if you are in the interface, the majority agrees with you, and there is one or two guys who do not, but you still get reinforced less than the others. Okay? And here we can see the same thing, but with a strength of opinion associated to it. So darker colors mean the opinion is stronger, lighter colors, they happen in the interface, of course. So, but how do we get there? Well, it's very simple. Let's start with this probability that we introduce for each one. And then let's assume that when I observe a neighbor, when an agent observes a neighbor, it assumes that there is a larger than 50% chance that that neighbor will pick the best choice. Okay? You trust your neighbors. If you do that, we can introduce this probability that your neighbor is basically correct. It's a conditional probability. If A is better, there is a probability greater than 50% that your neighbor J will pick +1. Okay? If B is better, this alpha and beta could be, and usually in most simulations they are the same, but they do not need to be. You could have a situation where you don't expect people to do something. If they are nice to you, if they are mean to you, they really don't like you. But if they are nice to you, you don't know. For example, it's not symmetrical in this kind of situation. People tend to be nice to you, whether they like it or not, because we are polite. But if they are not nice to you, it's because they don't like you. Then the probabilities are different. Okay, so there are circumstances where this could be different. And it's good to put it here because you have something that's already starting to be a little less toy and a little more similar to the real thing. Okay? So, but what we have here, since we have a conditional probability, is that what we really want is that what each agent wants to know, what's the probability that A is actually better, given that I observed this from my neighbor. It's the opposite conditional. So I can use Bayes' theorem, starting with the initial probability, apply Bayes' theorem. I'm not remind you how to do that, but you can do that. And then we have, once we observe, once you observe the neighbor is observed, you have a new probability T +1, a new probability also for B. Of course, it's one minus the other, so I don't really need this. But what's good is because we have the same normalization factor, I can divide them. So I can get some very easy simplifications when I divide one by the other, and I calculate the odds of one. So it's 2 to 3 odds, 2 to 1 odds in favor of one or the other. Okay, and then I get a multiplicative model here. But if I take the logarithm, I have this log odds that is just adding a term that is different if it's A or B. If alpha is different from beta, this term is different when I have observed for one or for the other. If they are the same, they just change the sign. So I can renormalize that so that this will be 1. Okay, just divide for something, redefine this, and then I get my initial formula that is just trivial model here that I just had to subtract 1 and do nothing else. But it's based on considerations that each agent makes about the chance that the other agent might be right. And that's what is interesting, because I can work from there and make more assumptions. Just, okay? Yeah. This here? Yes. I'm using this to... Yes. Each neighbor has a probability that A is the best choice, okay? At t equals 0. If you think that A is 60%, you can think, for example, you are an agent. So there might be 60% chance that you think A is better, so 40% chance that B is better, okay? That's for you. For he is the opposite. He thinks 65% B. Depends on the site, exactly. It's each agent I has one probability it assigns to, in each site you have one agent who is thinking about this, okay? And then you observe him, and he thinks that B is better. You think A is better, but you observe him, and he thinks that B is better. Yes, exactly. When you observe the other agent, when an agent observes the other, it updates its opinion, and that's what I call T plus 1. In the next instant, its new probability assigned to that option is... Sorry? No, it's not tipping. There is no tipping here. This is an internal opinion. It's the chance that the agent assigns to the possibility that A is better. Okay? It's not the probability that it will... you could have probabilities that it will choose A and represent itself as A. It's not that. If it prefers A, it always says, I prefer A. But it has an internal probability that measures how sure it is about that. Okay? And that's that probability. It's an internal probability not observed by others. I could make it observable. I did it in another paper. That's another question. But this is... sorry. But this... but this probability is an internal characteristic of each agent, okay? And when it crosses the 50%, that's when the agent flips. If it stays all the time the same size of side of 50%, the agent never flips. Okay? So yes, there is a flipping, but this is not a chance of flipping. This is a chance that the agent assigns to it being right. That's what I wanted to put those formulas here, because this is a part that never really gets through, because I am doing a few different things here. So it's a great question, because yes, it's not the usual way to make these models. Okay? Perfect. It's good that we stop here, because then the rest is easy. If you understand that, it's everything easy. But you have to understand that I'm doing a few things that are very, very different. Okay? So then I can make simplifications. They are trivial. Logarithms become, you have an additive model. I can use a normalized log odds so that I have plus and minus 1, and easy. If I have alpha different from beta, as I said, it's, people tend to be nicer than to be mean and things like that, then I can have different values in the addition and the subtraction. So we have that surprises can have a larger impact than no surprises. What does this mean? It means that when someone is nice to you, you say, oh, maybe they like me. But you're not so sure because everyone tends to be nice. But if they are mean to you, yes, this will really move your probability much more because it's a surprise. So you can have difference in effects from surprises, for example. Okay? Just as we should. If I change alpha and beta, this happens for these values of alpha and beta. Okay, here you see that this is expected. As alpha, you always expect them to almost always. If A is better, you expect them to do that 8% of time. But if it's B better, you only expect them to act 40% of the time. So it's really, there is really an effect of surprising. You are not expecting that. Okay? This allowed me to say, okay, so I can use that as a general theoretical framework for opinions, where I can define an opinion as a subjective probability on any issue. I have a random variable x, and people have a probability distribution of that variable. This represents the agent opinion that about each possible value of x. Can be a discrete function like with just plus and minus 1, but it could be, as in the bounded confidence models, a range between 0 and 1, and you say, I think it's more likely that values near 0 are the correct answer than the values near 1, for example. And you can have a probability distribution over this range. And it represents my opinion about that random variable. Okay? And then you observe someone who communicates you something that depends on their internal opinion. Not in the CODA model. What is the rule? If the opinion of the agent is larger than 50%, it supports that, okay? But it could be different. As he said, it could be a flipping probability. It could be that I could express my opinion that A is better is 60%. Instead of saying I think A is better, I could say I think A is better with 6% of chance. It's a different communication. I'm speaking different things. I'm giving different information from my neighbor. Okay, so I can assign a variable. Each agent has their own inferences about that. They have subjective opinion about X, and this represents how likely they think each value is. Okay. Communication. Oh, sorry. Okay. Here. Communication is a functional because it depends on my function of probability. So I will say something that depends on my probability distribution. So it's a function of a function, okay? And then but it can be very simple. I can and then say +1. It's just a general thing. If I want to do anything, okay, then I have to think about how I communicate. It does not need to be intentional. It can be an observed behavior. It can be what I express. What I express can include falsehoods. You could, in principle, put all those things there for the general thing. Then I need a mental model, and that's the very, very important thing. Here, what's the mental model? When I observe that you have an opinion, how does that relate to the possible values of my random variable? I mean, meaning this: if the correct value of the random value is 0, what are the chances for his opinions to be each possible opinion? If it is 1, what are the chances? If it's 2, and so on. This will give me those alpha and betas, but now possibly for a continuous space. Okay. I only had alpha and beta in the beginning, but now I have this over the continuous possibilities. From that, I can use again base theorem for discrete variables, for continuous variables. It works the same. It's a probability. And then calculate the new opinions for each agent about those. Update that, and from that update, they will decide, or they will communicate different from then on. Okay, that's the general model. Works for all of them. So I will have a new representation here for how my opinion in the next iteration depends on my initial opinion and my mental models. Okay, this has to be renormalized. If I can make that division and calculate odds, I get rid of the renormalization, but that's not always possible. Sometimes I have to really make this add to 1 in the end, or integrate to 1 in the end, because these are probability functions, okay? Sometimes I have to worry about that. If I can get rid of that proportional, great. That does not always happen. Sorry? This ain't... Okay. Yeah, I'm assuming that these AJs are what is communicated by agent J. Yes, you could have, I never thought of it, but it's an interesting question. You could have that J opinion might depend on the opinion of other agent. Yes, no, it's not true that I never thought about that. Let me show you the next slide, because it's related to that question. It's the one case when I consider that. AJ could be completely dependent only on the opinion of agent J, but opinion of agent J could depend, for example, on my opinion, because he's my neighbor. So I look at him, he looks at me, you look at me, I look at you, and the fact that you have the same opinion of you as I do might be because that's the best choice, but might be also because I influenced you. Okay? And I can introduce that in the mental model of my agent. If I do that, here I will have a probability that need to be replaced by a pair, because it depends on the probability that that the agent own opinion is +1, or the agent own opinion is -1. In this case, A was still independent, okay? Because it was what I observed from my neighbor. But A could be also, I could be observing 2 or 3 agents at the same time. And in this case, like in a majority model, I could be observing many agents at the same time, and then A would be a set of opinions. Okay? So we have, in this framework, I have the freedom to introduce many considerations that might be necessary to model different problems. For some problems, doing the most simple toy model is great. But sometimes I might need more. What's interesting is when I do that, is that if I consider the limit, when the agent own opinion on its neighbors is very, very strong, if I make it, if I take the limit when it's basically to infinite, the agent only changes its mind, basically, when there is disagreement. So we revert to spin models when you update discretely just from disagreement, because you don't have strength of opinion to reinforce. So when there is, you can have voter rules, you can have majority rules, you can have Schneid rules for those who know what I'm talking about. But again, sorry, this is getting weird. But anyway, I can introduce then, I can get this limit where I get the other discrete models, okay? I also use it, I don't think I have much time, so I will go fast now, because I want to talk about a bit about networks. So if the basic idea that I wanted to talk is a bit more clear, I will go much faster. I also did that introducing things that are exist in the literature, like contrarians, inflexibles. Here in inflexibles, we studied something where we are observing opinions in a group. So A was the majority, the number of people that agreed in the group. I also extended this to a bounded confidence-like scenario, where instead of a threshold, fixed threshold, there is a Gaussian, and you start to not really trusting people following a Gaussian, and you have very similar results. Okay. Then I worked with variations of code where I changed both the mental model and what is communicated. As I say, I can communicate the +1 or -1, or I can communicate the 6%, 80% in favor of A, 20%. And I can have different models, mental models here, because I might be looking for the best choice, or I might be looking for the best mixture. So the answer could be, I'm fine if the best answer is 60% of A and 40% of B. Because then my opinion is over a range, it's continuous. It's not my +1 and -1, but it's over the range. It's interesting to see that, well, here there are technical. You have very, very distinct questions on how extremism arises. When you express your probability, extremism explodes in a way that is, you can see here, we go to, I don't know if you can see the numbers, but here we go from 0 to 300, here from 0 to 40, 0 to 2, or 0 to 10, 37. Okay, so it makes a little bit difference in how strong opinions are in the end when you can go to the 10 and 37. And note that to translate this to probability, because these are log odds, you have to take that value and do E elevated to that value. So it's E, if you want to translate this to a probability, it's 1 minus E elevated to 10 to 37. It's that, here you have, here E to elevate to 2. So, okay, that's the odds that you are right. No problem. But you can have absurdly extreme opinions depending on what we do. Okay, if I introduce M choices, just to be sure, we can make beautiful maps. Here I have 10 different possible choices. Here I have choices over the dimensional level. Here's where I observed that there is difference between the definition of extremism as I spoke first. So I'll go first here also. But here, green means that you have a central position on a one-dimensional political scale with 5 possibilities, from red to blue, okay? Green, you're a centrist, but you can be a very strong centrist. And depending on the parameters, centrists might win, or almost everyone might be blue or red, okay? And then we get to networks. I had a student, I forgot to put his name there, he will kill me, Daniel Savoy. He was a student for, he did master with me. This is from his dissertation, okay? And he studied among many other things, but it was how opinion dynamics change over different networks. And in case of the CODA model, he observed that if you have more clustering, or less clustering, CODA model can lead to 2 cheap types of end result when if you differentiate them by how many people support the majority in the end. It freezes, but if the there is a lot of clustering, and your neighbor of your neighbor is also your neighbor, you will have that both A and B will tend to go around 50-50%. But if if you go to other networks where you have an effect like a hub, that hub can be very, very influential, of course, and then it can flip most of the network to agree with it. If A or B, doesn't matter. Here is the majority, regardless of it is A or B. Okay? Sometimes it was A, sometimes it was B in the simulations. But he picked the mean value of the majorities. So you will have important effects depending on the type of network that you're using, on how large the majority will be in the end. Okay? I also did that introducing trust, and that trust is basically this, as I talked in the beginning. There is a chance that my neighbor knows what he's talking, but I also have a chance that some neighbors might not know what they're talking, so they will give me the best answer, for example, with less than 50% chance. The important thing here is that this should be larger than this. It does not necessarily need to be larger and minor than 50%, as long as they are different, because there are one type of agent that you trust more. Okay? If you do that, I have different I cannot get rid of the normalization factor, so things get ugly, and I no longer have my +1 -1 model. I have this, and I have to implement this. And it's not so beautiful anymore, but there are a few interesting things, because here I can have not only the opinions are updated, but how much each neighbor trusts each other. So I can also see how trust evolves with this. It co-evolves with it. So if we have agreement or not, so when the standard deviation of opinions is 0, means that everyone agrees. Okay? Depends on the number of agents, the initial conditions, if they started already agreeing or they are extreme conditions. But what is interesting to us is that for certain, is that we have networks of trust emerge as a result. Okay, in this case, I was just plotting what happens connecting everyone who trusts the other more than 0.65. They started with this trust of 0.6, okay? So this means more trust than initially. So initially, nobody here, if I put 659 here, they will all be connected. Okay, if I put 80 here, they will take longer to connect. Okay, so this induces the evolution of a network of trust. And you see that at first, you have that people with opinion +1 and -1, they still have some kind of trust between them. But this disappears in the end after, because they start to distrust each other. Okay? For this case where the consensus do not emerge and things like that. So here we have an interesting effect from this network. And then I decided the paper that I really wanted to talk about here, and I have 3 minutes. But I decided to really make the opinions change together with the network. So what did I did? I started with a lattice. Everyone put spatially on a lattice. But who will connect with whom depends on the distance, so that I will have an effect that is not only opinion. I could have it a random network initially, depending on the degree of connection. But I started with them spatially connected, and then opinion evolved according to the CODA model. But I also, after K updates of opinion, I would try to rewire the network based on how close the sites were and if they agreed or not. Okay? And how I did that, I just very simple Metropolis algorithm where I calculate the change of energy and then accept it with a probability that depends on exponential of the change of the energy. Traditional, very traditional stuff. So, as we don't have, here are two cases of what we get from that. Here, when J, if you remember, J is the strength of the opinion term. Okay? So when the opinion term is less important, we still have the square lattice structure, very visible. Okay? And then when you make the opinion matters more, we destroy the lattice, the spatial structure. If I increase this more, they might even get disconnected. Okay, if I allow this connection in the algorithm, they might even get disconnected. And there are some, I also just played with measuring what was happening. So for different values of the parameters, the percentage of clustering increases with beta, obviously. The mean distance, they also increases with beta. They become much larger here. But there is a very different regime when you have opinions that are, when the opinions really matter, okay? Because then it's the same thing. And here we have the interface proportion. That means how many agents interact with others who disagree with them. And that's what I mean by interface. Okay? So that was it. I think I got in time.
Okay, thank you, André.
You're welcome.
Questions? One question.
I have a question about the influence of the initial conditions versus the network. Going back to prior to the coevolution part, let's say we have fixed networks, okay?
Okay.
If you have a fixed network, you can have multiple different final states depending on the initial states depending on your initial condition, right?
There are some things that are fixed. You have a tendency to, if you have a network with neighborhoods, then we will have a tendency to have local reinforcement in this model. So you will not go to consensus, basically.
Oh yes, no, I understand. So you could have different communities.
You have different communities. If you change the network, if you make they're just first neighbors or second neighbors, and this changes the visualization. You see that the domains became larger.
Let's say we have one network, one fixed network, one network realization. Nothing changes in that network. I changed just the initial distribution of probabilities, the initial condition. I can have different final states.
Yes, in the sense that if you usually I would put them randomly. Okay, and then when you do that, they will have a slow formation of domains. But if you start
different random assignments will give you different final.
Yes.
Okay.
Yes, but if you assign with not random initial, for example, you define random, you define the domains from the beginning. They tend to be reinforced from the very beginning.
Or you choose the hubs to have a particular.
Yes, if you choose the hubs to have particular, you can also make one hub, two hubs, one for each opinion, and that changes also the dynamic.
And now the real question that I want to ask: are all the final states always fixed points, or you can have oscillatory behavior that never converts to?
That's a good question. They tend to be almost fixed. They tend to be almost fixed points, in the sense that the final structure of the network, it tends to not change, except for very few guys, depending on the network that you create. So if you have this, just this, if this guy is, for example, +1, +1, +1, -1, and -1, this guy can flip. He can keep going and coming. So this guy might not be fixed. So you might have, but everyone else is getting reinforced.
But that's only going to happen if you have hardliners that are...
Yeah, exactly. So basically, you get to a fixed position. But I will not say it's perfect. That's what I must qualify it. Because you will, if you play it for a very, very long time, you will still see a flip here or there. But mostly, you see what happens in politics. People freeze and and stop. But then if you, I try other things. I introduced memory in a most recent paper. There are many things to be done there, but.
Other questions?
Hello? Hello?
Yeah.
Hi, thank you for your presentation. So the rationale of your model is really interesting. You have this mental process and the opinions, everything. So I'm just wondering how to obtain data to validate this kind of model and then trying to make inferences in real life.
That's a very, very important question that people in the whole community of opinion dynamics did not try to answer for a long time, except one or two people. There was surprisingly, there was a validation that's almost, I'm not sure if 10, 20 years old, from one model from Serge Galin, a French researcher. And he used his model in opinion dynamics to predict the outcome of the vote about the French accepting or not the European Constitution. And everyone was sure it would be accepted if you asked it the 6 months before. All the polls, even who was against it, will say, well, we will lose. And then he ran his model, and it predicted that the Constitution will not be accepted. And it went month by month according to what he had predicted. And then in the end, the Constitution lost. So this is a type of validation. Of course, not necessarily for his model, but that there was something in his idea that captured what would happen there. Maybe in other curves. But one way to do that is looking at this kind of data, voting. We did, some time ago, a test for the adoption of new technologies in hospitals, and we got a curve that was adoption curve that was closer to the actual one than the ones in the marketing books that assumed that was a Gaussian and nothing else. Okay. We have also seen this applied. The CODA model adapted and applied to the consumption of cigarettes by young generation. And I have a PhD student who is now in Dublin, and he did, and he's applying this kind of not just the CODA model, but this kind of modeling to the use of green spaces by the population, the areas to exercise and things like that. And they want to promote that. He's in the School of Health in Dublin, doing things like that. So this is. But we still have a long way to go to see which model is the best one, which model really works. Because there are questions about human rationality that I did not mention here. And humans are close Bayesians, but they are not perfectly Bayesians. On the other hand, they are better Bayesians than most of the literature will tell you. And I will argue that from my own work. So there is a lot of things here to support this and that still need validation. Okay.
Okay, one last question there.
Hello. Thank you for your talk, first of all. And I just wanted to ask if you can mention again how does the evolution of the trust network occurs in the model that you showed in the end. It was kind of fast. I couldn't.
I know.
Go to the detail. Thank you.
I wanted to make it very clear how I did things, so in the end, I didn't have a lot of time because it's not traditional. This I'm not using it. I can make the comparisons with spins, but it's not really that. So what you have happened here is that I have an equation for the update of the trust. Because when people look at their neighbor, they say, the neighbor supports A. This will make me more likely to support A, probably, if I think the neighbor knows what he's talking about. But all of us, I think, can think of someone that if that person supports A, you think, oh, maybe I'll go with B. Right? Maybe a politician, maybe, but everyone can think of someone like that. So it's not necessary. It depends on how it's trusted and how you think it's likely that that person will give you the best answer. So I introduced only two types of agents. Each agent is not a continuous. They consider that there are two types, one that's more reliable than the other. And depending on the value of these parameters, that's for more reliable neighbors and less reliable neighbors, there is this probability tau that agent is this type. Okay? And as it's the probability, I can also update it using Bayesian methodology and using all those techniques I did before. And then I update it to get not only a formula for my new probability for A and B, but also for in here, notice that is the opinion I have about J. So it's not symmetrical. Okay, this is not a symmetrical matrix. So there are lots of things to speak here that I did not have the time. But then I can see how this evolves for each one. And then I have this graphics that are directional because the tau is asymmetrical. So these graphs here are directed actually. Okay? So, and that's how it happens.
Okay.
You're welcome.
Okay, thank you. Okay, so we are running a bit late, so let's thank Andrea again. So now we have lunch, and we come back here at 2:30.